All right, we're gonna look at this optimization problem here. Pretty classical problem, I would say. The squeezing in the largest possible whatever shape they give you, in this case a right cone that fits in a sphere of radius 1. I will do my best to create an illustration here, but no promises. So, sphere, now kind of, without shading and whatnot, kind of hard to picture a sphere, but I think when I try to squeeze in this cone, it'll work. And let's do a couple pictures just to kind of simulate, this right cone idea. All right. So if I had a cone to fit in here, I'm just going to, for convenience, orientate this cone to where the tip um, fits at the bottom. Okay. Obviously, we could rotate and picture it elsewhere, but suppose this cone, you know, I thought maybe this would be the largest cone, the volume, that I should say, of the cone to squeeze into this sphere, right? And probably not. Let me just do another picture to show, but maybe, I don't really know, right? Hard to picture. My guess would be probably closer to, if you picture like an equator, right? Because then it's wider. My guess would be that that one is more volume than the previous one, but I don't know. So that's the idea, right? What dimensions should I make this cone to have the largest volume, but it's constrained, right, by this sphere with the radius 1. Here's the tricky part, I think, is the sphere does have a radius 1. How does this really fit in this picture? I mean, the volume of a cone, so let's write this formula here. The volume of a cone, volume, and then, so the right cone just means, um, if I drew a line from the tip of that cone up, it would meet at a right angle. Okay, so it meets like that. So, well, are all cones a right cone? No, because this slanted cone, it's something like that, is still a cone. But now if I were to go from that vertex, we'll say, up to the center of that cone, right? You drop something from the center of the top circle down to the bottom, it is not hitting at a right angle. Okay, the radius and that line would not meet at a right angle. So that is right cone. Let me go and erase that. We don't need it. Okay. The volume of a cone, right cone in particular, 1/3 pi r squared h. Um, where this diagonal is h and then this is our r. Okay. So the sphere, volume of a sphere, do a little shade in there to show it's not a circle, whatever, is 4/3 pi r to the third. Okay, 4/3 pi r to the third. But those r's are different, right? And you could easily tell, since I drew 3 different cones here to kind of help picture, like this radius on the top one is not the same radius as the sphere, right? Because if you picture this one straight down to here, I could see that radius is 1, and it's a little longer, right, than that radius I drew there. But the trick is, if I were to picture this rotated to that point here, where the radius of the cone meet, that is still 1. If you see that is probably the most helpful piece to get going on this problem. In fact, I think I looked it up too. I can't remember. Off the top of my head, it's been a few weeks, but I did want to create a video for this one. Pretty classic problem. Okay. Well, how does that help? Well, I can also see from this center point of the sphere down is 1. So h overall, if I knew, we'll draw this little piece missing here. If I knew that piece, then I know my h, right? And if I just call that piece x, for instance, because I don't know it, then I know my h would be 1 plus x. I still don't know r for the cone, but notice we do have Pythagorean theorem happening here on this. Let's highlight it in green, right? We have this little right triangle there. So sticking with that green color, I know that that is 1 because that was the radius of the sphere. I have a right angle. I don't know this r, that's what I'm going for, and I have this x. Okay. Now why is that important? Well, if I can get everything in terms of a single variable, and optimization means set the derivative equal to 0, right? And I'm trying to optimize this. I'm trying to find the largest cone. So if I could do that derivative and set it equal to 0, perfect. And the problem I have now, though, is I have 2 variables. So if I could get them all to be x, we can finish this problem. And we can do that because I have h in terms of x already. This piece is done. So now let's use Pythagorean theorem on that piece above to get r, right? I'm solving for r in terms of x. X squared plus r squared equals 1 squared. So therefore r squared is 1 minus x squared. And r, I don't need the negative root because it's a distance, right? So I only care about the principal square root. The positive is square root 1 minus x squared. All right. Let's get going then. So the volume is 1/3 pi r squared. So I have, making this substitution, I have square root 1 minus x squared. Squared, right? It's r squared times h. So times 1 plus x is my h. Okay, looks good. Yeah, I agree. Square root 1 minus x squared squared. Let's simplify this thing. So we have 1 minus x squared, square root and square cancel, times 1 plus x. But, well, up to you, right? You could do derivative with product rule at this point. I know 1/3 pi is constant, so I could just leave that. Maybe that's easier. Maybe you want to distribute. I don't know. Sometimes you're going to run into an evil either way, right? So 1/3 pi, I'm going to go in a FOIL. We'd have 1 plus x minus x squared minus x to the third. Okay, now let's do derivative. V prime. Again, 1/3 pi is constant. Let's just leave that there. No point in distributing that and then having to mess with it. So derivative of 1 is 0. Derivative of 1 is 1 minus 2x minus 3x squared. All right, that's my derivative. And to optimize, we need to set that derivative equal to 0 to find critical points, right? 1 minus, so, okay, I'm going to rewrite it. And then we'll factor out a negative and go from there. So keep in mind, this is derivative. Does this thing factor though? I think it does. Let's go ahead and try. So 3x squared plus 2x minus 1, and then I'd have 3x and an x, and yep, plus 1 minus 1. Okay, I like the factored form when we set the derivative equal to 0, because then if I need to test any critical points, it's really easy using that. Okay, so I'm going to highlight this, kind of keep track of that. So our two critical points, we have x equals 1/3, right? Or x equals -1. I want to make sure I have a max here. And remember, with optimization, you do have to think of your boundaries, but I don't have a closed interval in this case because at the extreme, right, r could be 0 or h could be 0. But so at the boundaries, if r is 0, then h, could be the entire length, but I wouldn't have a right cone. I would have a line, really, right through this equator here if I didn't have a radius. And likewise, if h was 0, then I would just have all of the length there for the radius, and I wouldn't have volume. So really the boundaries don't exist, and I don't need to check boundaries in this problem, but it's always important, make sure, right? Make sure to check if they do exist. So on that note, x equals -1, that wouldn't even make sense, because then looking back at that picture, right, if x is -1, first off, it's a distance, but -1 and 1 is 0, so h would be 0. That doesn't make any sense. So 1/3. If x is 1/3, check your boundaries. Again, we want to make sure this is a max because we're trying to maximize volume, right? Find the largest volume. So I could check 0, right? All I care is, do I get a positive or negative? So I'd have a -1/3 pi, so I'd have a negative, plug in 0, we'd have a negative, plug in 0, we'd have a positive. Negative times a negative times a positive is positive, so increasing. So now I hope whatever number I check here, greater than 1/3, I'm going to check 1, that I get a negative, that way it's decreasing, and I in fact know it's a max, right? That's my hope. So let's plug in 1. We'd have a negative times, let's see, 3 times 1 is 3, minus 1 is positive, and then plug in 1 at the end, we'd have a positive, so we do get negative. Awesome. So the volume of the largest right cone, so the question is the volume. First off, x wouldn't probably fit anything, right? Like maybe it asks for the dimensions, the radius and the height. It's highly unlikely they want x because we drew this x in this picture, which is only from that 1, right? From that radius of 1, I went an additional 1/3, so therefore the height is 4/3. Okay, so the overall volume then, volume equals 1/3 pi. Okay, we still need to think what r is, so we do need, I'm going to go ahead and write the formula one more time. Okay, I know h, right? H is 4/3. Okay, kind of see that by looking at the picture. R, remember, is square root 1 minus x squared. So let's kind of do that on the side here. Scratch is square root 1 minus x we got is 1/3 squared. So 1/9. So therefore r is square root 1 minus 1/9, which is 8/9. And if we reduce that, you can, but I'm going to pause there because the formula has r squared. So if I'm going to square a square root, what's the point of reducing it, right? So let's substitute that in. We have 8 over 9 squared, 1/3 pi, and multiplying that through and wrapping this up, we have 1/3 pi times 8 over 9 times 4/3. I wish that something was going to cancel, but it doesn't look like it at all. So we get the volume is 32 pi over 81. And what units are we in? Well, it doesn't give me any unit, right? But we are volume, so whatever that unit is, cubed. Awesome. That's a pretty lengthy problem, classical type of optimization problem. Hope that helps you out.